This lesson deals with a CMOS NAND gate. You can find these notes in the ECE302 ebook in Chapter 4 on page 45. Take a look at what's called a CMOS NAND gate, where I've got this configuration of MOSFETs. These two are in parallel, are sharing the same two nodes, and when we have a logic gate using MOSFETs, they're either a high resistance or a low resistance. So I'll show this resistance as R sub SD1 and R sub SD2. For transistor 3 and 4, they're in series. I'll call this R sub DS3 and R sub DS4. When we have a 5 volt power supply, these inputs can either be 0 or 5 volts. In our last video, we took a look at a little different technique for taking a guess and verifying our guess, and that was to assume that the current in the circuit was very small. We're going to assume that this is small, and by that I mean nanoamps or maybe picoamps. And then if that's true, can we find the states of the transistor, and then can we go back and check that this current is small. To make things easier for the algebra, let me pick the threshold voltage to be 1 volt. Take a look at the first case below of having 0 volts and 0 volts. Finding the source to gate and the gate to source of the outside transistors is usually the easiest, so this is a gate source voltage of 0 from this. And then here I've got a source to gate voltage of 5 volts minus 0, so this is 5 volts. And likewise over here I have 5 volts and then I have 0 volts, so the voltage between here and here is 5 volts. If we're less than threshold, we're in cutoff. Make this a big resistor, say maybe 1 gigaohm. And again, I'm just guessing at the value. And when the source to gate is greater than threshold, it's either going to be ohmic or current saturation. But because we're assuming that the current is small, we don't have enough current to get into the saturation region. This would be an ohmic, pick 1 ohm. And likewise for this one, 1 ohm. What's the voltage here? If I can find this voltage, I can find the gate to source voltage at transistor 3. I've got a small current flowing, and I've got a big resistor here, so the drop across here can be anything, but I am limited to a 5 volt power supply. So this node voltage here is somewhere between 0, I'll call it V sub x, and 5 volts. If this voltage is 0, and this voltage here is, say, 5 volts, it's a minus 5 for the gate source voltage. If this was 4 volts, I'd get a minus 4. If it was 0, I'd get 0. Even though I don't know the value of this voltage, I do know that this transistor has a voltage here that's less than or equal to 0 volts. And that puts this into cutoff. It would likewise be a big resistor, say 1 gigaohm. I can solve for V out. It's a voltage divider of 5 volts times the resistance here, which is 2 gigaohms, over 2 gigaohms plus a half an ohm. And this, of course, dominates the denominator. Got basically 1, so this is about 5 volts, really 4.999. Two inputs of 0, output of 5 volts. I should also mention here how the bulks are connected. You can see that the bulk of the P-channel device is connected up to the most positive potential in the circuit. And for the N-channel devices, it's hooked up to ground, which is the most negative potential in the circuit. Lastly, let's check if our assumption about assuming a small current is true. The resistance seen by this power supply is half an ohm in series with 2 gigaohms. 5 volts, roughly divided by 2 gigaohms, is equal to 2.5 nanoamps. That is a very small current. Take a look at the next case where this is 0 volts and this is 5 volts. But for me to do that, I need to erase all this stuff here, so let's do that. Our next example is having 0 and 5 volts here. And let's find the gate to source and source to gate voltages. So that makes the gate to source voltage here 5 volts. The source to gate voltage here is going to be 5 minus 0, so it'll be 5 volts. But now the source to gate voltage here is going to be 5 minus 5. That's going to be 0 volts. Having 5 volts here, we're greater than threshold. If the current is small, we're then in the ohmic region. That would make this a very small resistor. And again, just pick 1 ohm. Same is true up here. I have 5 volts, so I'm greater than threshold. So this would be in ohmic, roughly 1 ohm. But now here, I'm less than threshold. That would put me into cutoff, and that maybe be a big resistor, say 1 gigaohm. And now we got to figure out this gate source voltage here. If I have a small current, the voltage across here is going to be small. In other words, if you had a nanoamp of current and a 1 volt here, you'd have a nanovolt. This voltage here is roughly sitting at 0 volts. This is sitting at 0 volts, and the gate to source voltage is going to be 0. That's going to make this less than threshold, and again a big resistor, say 1 gigaohm. Let's check our assumption. Here I've got roughly 1 ohm in series with 1 gigaohm and 1 ohm. So I roughly have 5 volts divided by a gigaohm, or 5 nanoamps. And so that is small. That checks our assumption. Let's solve for V out. Again, we have a voltage divider. 5 volts. Here I've got 1 gigaohm plus 1 over 1 gigaohm plus 1 plus this parallel combination, and that's roughly about 1 ohm. That's going to be equal to roughly 1 gigaohm divided by 1 gigaohm, so that's about 5 volts. Input is 0.5. The output's equal to 5 volts. Take a look at the next case of having 5 and 0. Again, let me erase all this. Our next input in the table below is having 5 volts here and 0 volts. Gate to source voltage here is 0. But now here our source to gate voltage is 5 minus 5, or 0. And our source to gate voltage here is going to be 5 minus 0, or 5 volts. This being less than threshold, that would make this in cutoff, so be 1 gigaohm. Likewise here, this is in cutoff, so 1 gigaohm. And this is greater than threshold. I've got the minus sign here. Here's the plus and minus. That would make this a low resistance, say 1 ohm, because the current we're assuming is small. We have the trouble of figuring out what this voltage is, so we can calculate the gate to source voltage of transistor 3. I have a small current and I have a big resistance. Big number times a small number can be anything, but this node is somewhere between 0 and 5 volts. If this voltage were 5 volts, 5 minus 5 would be 0. We would be less than threshold. If this was 4 volts, we would have 5 minus 4, or 1. We would be right at threshold. If this was 3 volts, we'd have 5 minus 3, or 2 volts, and that would be greater than threshold. We don't know the value of this resistor. It could be a high, it could be a low value. And I'll label this as a don't know, and we'll see what impact that has on our calculating the output voltage. But before we do that, let's just check that the current is small. These two in parallel is about 1 ohm, but that's in series with an unknown resistor and 1 gigaohm. The 5 volts is divided by at least 1 gigaohm, so we're looking at something in the nanoamp range. Our assumption checks. Let's solve for V out. It's again a voltage divider. In fact, all logic gates with CMOS are voltage dividers. It's going to be the don't care plus 1 gigaohm over the don't care plus 1 gigaohm plus roughly just 1 ohm. The parallel combination is the smaller of the two. And my numerator and denominator are about the same size. So this is again about 5 volts. If I have a 5 and a 0 input, the output's equal to 5. Last case is having 5 volts and 5 volts. Let's erase this so we can take a look at that one. Our last case again is 5 volts and 5 volts. Gate to source voltage is 5. The source to gate is equal to 5 minus 5, or 0. And here the source to gate is going to be 5 minus 5, or 0. Here we're greater than threshold, so that's going to put this in the ohmic region if the current is small. Here I'm in cutoff, so this would be 1 gigaohm. Here I'm in cutoff, that would be 1 gigaohm. And now can we figure out what this node voltage is here to calculate the gate to source voltage for transistor 3. Having a small current and a small resistance, that makes this voltage here very small, or about 0 volts. This is around 0 volts. The source to gate is about 5 volts, which is greater than the 1 volt threshold, so that would make this a low resistance, say roughly 1 ohm. Let's check our assumption. 5 volts sees these two in parallel, which is a half a gigaohm plus 2 ohms. Seeing something again in the nanoamp range. V out then is equal to 5 volts times 1 plus 1 over 1 plus 1 plus these two in parallel, which would be a half a gigaohm. We have 2 divided by 1/2 gig. Throw this away, bring the 2 up in front, so I have 10 times 2 divided by 1 gig. I have a very, very small voltage in nanovolts. It's approximately equal to 0 volts. Both inputs high, the output is low. Take a look at a table below. Here's what we just did in the previous cases, plus this one. So we had a less than or equal to 0. We had don't know, just like we did for the NOR gate. And here's our output. It's 5550 for the different combinations of input. When both inputs are 0, the output's high. One high, one low. Same thing is true, but when they're both high, it's equal to 0. And this is the AND function negated. And this is how a CMOS NAND gate works.